Welcome to ChemVid. Today we're going to go over phase changes, calorimetry, and thermochemistry, just as a review since we did it quickly as a group presentation in class. So first of all, this phase change diagram. If you look, the temperature increases this way and the heat energy increases this way. The difference between temperature and heat is that heat is the actual energy being produced, whereas temperature is the kinetic energy a molecule contains. Okay? So one is a measurement of the molecule, the kinetic energy, that's the temperature, and one is just if you're getting energy. It's just energy in general. Okay? So if I look at this diagram, I see that as I am a solid, I can increase in temperature. But once I go through a phase change, once I try to melt into a liquid or a liquid tries to freeze into a solid, during a phase change, the temperature does not change. It remains constant. It's the same thing up here when a liquid turns into a gas or a gas to a liquid. Always during a phase change, phase changes stay constant. So as I look at this solid, each individual molecule is moving back and forth and to the side. They're constantly moving. However, they're doing it very slowly because they're a solid, which means that the kinetic energy of each molecule is very low, which means that their temperature is low. Okay? If I look over here at my liquid, as you can see, my liquid is a bit more spread out, but these molecules are moving a little bit faster. And so their kinetic energy is higher, so I'm going to say the medium, which means their temperature is in the medium range. Then over here we have our gases. And you know that gases are in constant, random, rapid motion. They go really fast. So each particle has a ton of energy, which means that its kinetic energy is high and the temperature is high. Okay? So, that's the difference between the temperatures. As my temperature increases, the kinetic energy of each individual particle increases. But when we talk about heat, heat is how much energy is being put into the system, okay? So heat is energy. That's all it is. It's a type of energy, just like light energy or potential energy or kinetic energy or anything like that. It's just energy. So when I add heat to a solid, originally the heat is going to go to each of these molecules and cause them to vibrate a little more. But once they're vibrating at a certain speed, then instead of making each individual particle move faster, they actually start to push each particle away from each other, therefore turning into a liquid. So if you see, there's a bigger separation between the liquid particles than the solid particles. That's because the heat energy is going to make them separate. So during a phase change, the reason why phase changes are constant is because the heat energy is no longer going directly into a molecule, but is going to separate these molecules so that they can change phases. Once I've changed a phase and they're separated the correct amount, then as I add heat energy, they'll do the same thing. They'll start moving it more and more and more so that the liquid can pick up speed and each individual molecule can move a little faster and a little faster. And then again, the heat energy, as heat energy is continued to add, finally these guys will have enough kinetic energy, and so they will keep moving at this same speed, but now the energy will go into breaking these bonds, or these these forces between the molecules, so they can spread out so it can become a gas. And then you can add heat and it'll cause the molecules to move and move and move and move and move and move even more. So that's why temperature will not increase during a phase change. So as a review, freezing, vaporization, evaporation, condensation, sublimation, and deposition. You guys are familiar with the first four. Sublimation and deposition may be new to you, but it's just when a solid goes directly to a gas and a gas goes directly to a solid. I like to remember it as in deposition, sounds like deposit, so it's like you're grabbing all the gas molecules and depositing them into one form, a solid. The difference between vaporization and evaporation. They're both a liquid to a gas, however, evaporation is done without added heat, and vaporization is done with heat. Okay, so that's the difference between the two. We already talked about temperature. We already talked about what changes and what doesn't. So let's go over the examples. Ice water, when you have ice in your water, the ice water will stay the same temperature because while the ice cubes are melting, all the heat is going to spreading out those molecules, not to increasing the temperature. Whereas dry ice in a balloon, dry ice sublimes. So as I put a solid piece of dry ice into a balloon, the balloon will start expanding because the gas will push out. Next, we have our phase diagram. On this phase diagram, we see that pressure and temperature both play a key role in whether or not something is a solid, a liquid, or a vapor, or a gas. So if I follow this phase diagram, this is unique to every single substance. This one is water. So if I look at 100 degrees Celsius at 1 atm, see how it's lying right on that line? That means it's going to be a liquid and a gas. And if you notice, 100 degrees Celsius is the boiling point for water. So when I'm boiling water, some of it will be a liquid, some of it will be a gas, until I get everything high enough that the temperature just slightly starts to increase and we can overcome that pressure and it'll become a gas. Okay? The special thing about this one is the triple point. So a triple point is where all three of these lovely phases are at the same time. So they exist all at the same time. So this is a video of tert-butyl alcohol's triple point. So if I look over here, this is tert-butyl's diagram. Their triple point is at about, I'd say 20 degrees Celsius. And the pressure is about 32, oh, right there. Yeah, 29.8 torr. Okay? So what they're doing in this video is they are controlling what is going to happen. And they're trying to get it to 20 degrees Celsius. They're measuring it with a thermometer. And then they're controlling the pressure so it is 29.8 torr. So if you watch, you can see this is a liquid. And then if you notice right here, this is when the solid starts to form. So we have a solid and a liquid all at the same time. And they're continuing to change it. And look, there's the gas. So you have a gas with a liquid. We know it's a liquid because it's moving. And we have a solid all at the same time at a certain temperature and pressure. Every substance has a triple point, and tert-butyl alcohol's triple point is just easier to get to, and so therefore we use tert-butyl alcohol as an example. So every line represents two phases, and then the triple point represents all three at once. If I look at the graph, I can trace 201 pressure ATM. So 200 degrees is about here, 1 ATM is about here. It's in the vapor phase. So check yourself, see if you got that right. That's phase changes. Now, energy. Energy is the ability to do work. So it's what we use in order to do something. You might say that whenever you play a game or you do your homework or you do anything that requires you to actually work, you are using energy, okay? That energy can be measured in joules, little calories, or big calories. Big calories are nutritional calories and are 1,000 times bigger than little calories, okay? Joules are used everywhere else in the world. Calories are used here for measuring nutrition. So in our example, we had 130 calories. We used our dimensional analysis to go from big calories to little calories to joules, and we were able to get how many joules were in a Nutter Butter Bite. All right. The next part we talked about was the types of energy. Kinetic, potential, nuclear energy. But there are so many more. There's light energy, heat energy. There is chemical potential energy. There's chemical kinetic energy. There is static energy. There are lots of types of energy. These are the three that mainly come to mind, but there are tons of them, okay? So the difference between kinetic potential and chemical kinetic. Potential is stored in the bonds. It's the energy that chemicals have to react, basically. Whereas kinetic energy is where they actually break those bonds, and they make new bonds, and they react. So it's when they're using that energy. Law of conservation of energy, just like law of conservation of mass, energy cannot be destroyed. It just switches to different places. And then temperature is a measurement of kinetic energy. We already went over that. Glow sticks use a chemical energy. There's potential energy stored in the glow stick. When you break the glow stick, the chemicals mix together, changing it into chemical kinetic energy. And that energy produces light energy, okay? So they transfer, energy transfers. Same thing with your food. You eat the food, it turns into energy that you can use. The steel spheres is an example we'll go over in class. It's better if you see it. Now, calorimetry is the science of finding out how many calories or how much energy is in your food, okay? So when we talk about heat capacity, that's the amount of energy it takes to heat something up. Specific heat is specifically how much energy it takes to heat 1 gram of a substance by 1 degree. So if we look down here, our equation whenever we're trying to do heat is Q equals mc delta T, where Q stands for heat in joules, M is the mass of your substance, specific heat is the mass of the same substance, and change in temperature is the change in temperature of that same substance. Specific heat of liquid water, we're going to use that a lot, so I suggest memorizing it. 4.184 joules. So when we talk about systems, surroundings, and universe, our system is whatever we are watching. So in this case, it's the reaction. I have a reaction going on. My surrounding is the water surrounding my reaction. And then the universe is the entire thing. Woo! Okay, so my universe is my system plus the surrounding. When we talk about heat, we're talking about heat being absorbed or released. So if my reaction lets off a certain amount of heat, let's say 10 kilojoules of energy, my water must absorb that same amount of heat, 10 kilojoules. So on your notes, you see that the Q of the reaction is equal to the Q of the surroundings, and that's because whatever heat the reaction lets off, the surroundings has to absorb. The reason why one of them has to be negative is because that negative means that you are releasing heat, and the positive, that's not always written, means that you are absorbing heat. Okay? So, when you're looking at this, heat of the reaction is directly related to heat of the surroundings. That's why we can measure the heat of the surrounding area to calculate the heat of the reaction when we can't measure the heat of the reaction specifically. By the way, releasing is not spelled with 2 A's. Sorry about that. So the key to using Q equals mc delta T is to make sure everything is the same. For instance, in this example, this is the mass of the water, specific heat of the water, and the change in temperature of the water. In this example, because potassium chloride dissolves in water, it becomes a solution. So I need to use the mass of the solution, the specific heat of the solution, which will be close to water because it's mostly water, and then the change in heat of the solution. And then down here, all it wants me to do is to find the specific heat, so I need to rearrange my equation, and I will take 207 joules divided by the mass and the temperature in order to get specific heat. We will do the rest of those demonstrations in class. Here's a quick review. Come see me if you need help.